In this video, I want to talk about, I want to start talking about section 4.6. So what we're going to do in section 4.6 is we're going to take a matrix A. So we're back to studying matrices in a way. And we're going to split the matrix up in one of two ways. We can either look at the columns of A or the rows of A. So I'm going to start with the columns of A. And we can think of these columns. So A is a 2 by 3 matrix. We can think of these columns as vectors in R2. And so what we can do, and one of the things that we'll talk about is what's the span of the columns of A. Okay, this is sometimes called the column span of A. And we'll talk about exactly what that set is. We know that these are vectors in R2, so at most it can be R2. More than that, we actually know that the span itself has to always be a subset. So whatever the set is, this is always, so this is always a subset, excuse me, this is always a subspace of, in our case, it's R2. Okay, but it's R2 because this is a 2 by 3 matrix, and these are vectors in R2. So this is always a subspace of R2, meaning that it's either the zero vector itself, it's a line through the origin, or it's all of R2. And we just have to figure out which one. So that's really the only options that we have when we talk about this. This subspace has a special name. This is called, this is the column space of A. So this is called the column space of A. It's denoted. There's lots of different ways to denote it. Some books like to write COLSP of A. I will just do COLSPACE, just COL space of A. Okay, and so that turns out that it's going to be a particular subspace of R2. Now, since it's a subspace, that means it's a vector space in and of itself, and therefore it has a dimension. The dimension of the column space of A also has a name. This is called the column rank of A. Okay, so that's called the column rank of A. And that's again, the dimension of the column space, because the column space being a subspace means that it's a vector space and therefore has a dimension, right? You can find a basis and so on. So at this point, let's go through and let's do this example. Let's think about what's the span of these vectors 1, 4, 2, 5, and 3, 6. Okay, so I want to know what's the span of the set. And I want you to think about this carefully. We have 3 vectors in R2. So certainly the set is not going to be linearly independent, right? One of these columns has to be a multiple, it has to be a linear combination of the other two. No matter what, because we know that R2 is a 2-dimensional set, so any basis has only 2 elements. If we have 3 elements in a set, it's not a basis because it's not linearly independent. So really, we're using ideas from the 2 previous sections now. So the reason why I bring that up is that if I just ignore one of these columns, say 1, 4, 2, 5, notice that adding in this vector 3, 6 only makes the span bigger than the span of 1, 4, 2, 5. Now, what I'm going to say, I'm just going to tell you the conclusion and then how I reached it. The span of the set must be all of R2, since the span of these 2 vectors, say 1, 4, 2, 5, is R2. And adding in this vector, also adding in multiples of this vector 3, 6 can only make the span bigger. But in our case, it can't get any bigger than R2, so that's it. So you could do this by hand if you'd like. You can actually write out what are the vectors ST, where you can write them as a linear combination of 1, 4, 2, 5, 3, 6. Or you can just realize that 2 of those vectors actually span R2. Everything lives in R2, so that's as big as the span can get. So therefore, all 3 vectors have to span R2. Okay, it's a little bit of a subtle argument, hopefully not too subtle, but that's the idea. So since 2 of those vectors span as big a space as possible, then all 3 must also span that big space. So the span of the vectors is R2. That tells us that So R2 is going to be the column space of our matrix A, and therefore the column rank, the dimension of the column space, is going to be 2. Okay, so the column rank of A is going to be 2. This is important enough. I want to emphasize that there. So that's the span of the columns. And then we could play the same game. Let's take the same matrix. A is 1, 2, 3, 4, 5, 6. Again, a 2 by 3 matrix. Let's look at now the rows. So let's look at the row 1, 2, 3, and 4, 5, 6. And let's look at the span of the rows of A. Again, creatively called the row span, or the row space. So this is called the row space of A, because again, it's the span of vectors. In this case, they're vectors in R3. They have 3 components. We're thinking of R3 now as the set of vectors, say A, B, C, where A, B, and C are real numbers. And whether you want to think about it as the vector is the matrix ABC, or whether it's a column matrix ABC, those are both perfectly valid ways of thinking about R3. So the span of a set of vectors, because it's the span, has to be a subspace, and because it's a subspace, it has to be a vector space, and because it's a vector space, it has to have a dimension. So the this is going to be basically the same story as above. The span of the rows, otherwise known as the row space, is a vector space itself with a dimension. In this case, the set of vectors that we're working with will be vectors in R3, but there's only 2 of them. So the dimension can be at most 2, because there's at most 2 vectors to play with. So this is, again, called the row space of A. The dimension of the row space of A is called the row rank of A. And the row rank, again, we can compute by thinking about what's the dimension of the vectors here. And there's a few different ways to do this. So what we can do is we can think about, let's try and solve, let's try and look at, let's actually do this. Let's look at A times the first vector, 1, 2, 3, plus B times the second vector, 4, 5, 6. And what we want to do is we want to figure out what this is equal to for all vectors, say S, T, R, and R3. So we want to figure out what exactly are the vectors in R3 that we can write as a linear combination of these two. Now, clearly, we can't write everything in R3 as a linear combination of 2 vectors, because R3 is 3-dimensional, and that means that any set of fewer than 3 vectors, so any set of 2 vectors in this case, it can't span R3. So it's not going to be a basis. We can't get everything. We just have to try and categorize what can we get. And so it turns out that when we simplify everything, we're going to get 3 equations but 2 unknowns. So that's going to be A plus 4B is equal to S. I'll let you work out the details here, just simplify. 2A plus 5B equals T, and 3A plus 6B equals R. And we can think of this as maybe a matrix equation. That might not actually be so helpful, because it's not going to be a square matrix. So let's write it as an augmented matrix. Let's say 1, 4, 2, 5, 3, 6, augmented with STR. And again, since the coefficient part of this is not square, then we can't do things like talk about the determinant and so on, and that's not going to tell us about unique solutions. So what we need to do is just do this by hand. I will, I think, just leave it to you to do this. This is just basically now a chapter 1 exercise, albeit it involves the quantities S, T, and R. But after some blood, sweat, and tears, it turns out that the row rank of our matrix A is going to be 2. In other words, that's the dimension of the row space. So that's the dimension of the row space of A. Okay, so the row space is going to be a 2-dimensional object. In other words, the row rank is 2. Notice that the row rank and the column rank were equal. Okay, so notice that these 2 values were equal. And that's not a coincidence. It turns out that that's going to happen for every matrix A. So for every m by m matrix, A, it turns out that the row rank and the column rank will be equal. And so what we can do is we can talk about that common value and just refer to it, instead of thinking about explicitly in terms of the rows or columns, we'll just call it the rank of A. Okay, so the rank of A is just this row rank or the column rank of A. It turns out that for all matrices, that value, the column rank and the row rank are going to be equal, so we can talk about the common value and we'll just call that the rank of A. And so there's a few different ways that we can think about this. You can think of the rank of A as the dimension of the column space. You can think of it as the dimension of the row space. Alternatively, one other helpful way here, it turns out that the rank of A is going to be the number of pivots in the echelon form of A. What I mean by pivots, remember, is this is the number of leading ones. So this is the number of leading ones in the echelon form of A. I don't care if it's reduced row echelon form or just regular old echelon form. The number of leading ones or the number of pivots is going to give us the rank. And so what that tells us is that if we were to take our matrix A, and I think it's worthwhile doing this in this first case. So this is the matrix 1, 2, 3, 4, 5, 6. And let's look at this matrix and let's reduce it. And again, I don't care about reduced row echelon form. I'm not trying to make this as simple as possible. Although we now know enough information that I can actually quickly tell you what that's going to look like. But I'll say that at the end. So if I wanted to take this matrix A, so let's reduce it and let's put it in row echelon form. So what we'll do is we'll take -4 row 1, add it to row 2, and that's going to be our new row 2. So we're going to replace row 2 with -4 row 1 plus row 2. And when we do that, what we're going to end up with is up top we still have 1, 2, 3. Down below we have 0. Negative, let's see, 5 minus 8 is -3. And 4 minus 12 is negative, can't do this. 6 minus 12 is -6. There we go. And then what we can do is we can multiply row 2 by -1/3. So we're going to replace -1. Keep writing this backwards. We're going to replace row 2 with -1/3 row 2. And that's going to end up with the top row being, again, 1, 2, 3. And the bottom row being 0, 1, 2. Okay? And so this is row echelon form. If these were zeros, then this would be reduced row echelon form. Or rather, I'm sorry, if this was a 0, then it would be reduced row echelon form. But it's not, I don't care. It's just the row echelon form. And then the question is, how many leading ones do I have? And it turns out that there's 2 of them. Okay, so it turns out that there's 2 of them. Now, what I was going to say before about the reduced row echelon form is that I knew that if we were to do the reduced row echelon form, since these first 2 vectors span R2, this is going to turn out to be a 1, 0, 0, 1, and then with possibly some other stuff here. Okay, so you know that the span of it is going to be 2, just based on everything that we've talked about so far. Okay, so the fact that there's 2 pivots here, or 2 leading ones, tells us that the rank of A, so the rank of A is going to be 2. Okay, so that is the rank in a nutshell. We'll do some more examples in the next video.